Bismillah ar-Rahman ar-Rahim. Welcome everyone. Today we will talk about chapter 28, Sources of a Magnetic Field, lecture 2. In this lecture, we will discuss the following items. The outline one is Ampere's law and its applications. Item 2, magnetic flux, and then we will talk about the Gauss's law and magnetism. At first, let's introduce Ampere's law. According to Ampere's law, we can say that the line integral of BDS through a closed path is equal to mu naught multiplied by the current enclosed by the symmetric path. Ampere's law is valid only for steady current. What means steady current? A current that does not change with the time. That means a constant current. Ampere's law is useful for the calculation of the magnetic field of a current configurations having a high degree of symmetry. So let's repeat Ampere's law. The line integral of BDS, B is the magnetic field, DS is the line element, mu naught is the permeability of free space, the I is the current enclosed by the path. Okay, let me take another slide and explain step by step. Okay, so Ampere's law states that the line integral of BDS equal to mu naught I enclosed. Okay, good. So as you know, B is the magnetic field. DS is a line element. Mu naught is permeability of free space for pi times 10 power negative 7. I enclosed is the current enclosed by the path. What means this zero? This zero means that the path is closed. Okay, so what's the unit of each quantity? The magnetic field is expressed in Tesla, the line element is in meter, the current is an ampere, and of course mu naught is going to be Tesla meter over ampere. Good. So to apply Ampere's law, we have to satisfy the following steps. Step number 2, select the symmetric path around the conductor. Step number 2, write Ampere's law, line integral of BDS equal mu naught multiplied by the current enclosed by the path. Step number 3, calculate the left-hand side. Step number 4, calculate the right-hand side. Step number 5, put left-hand side equal right-hand side, and then calculate the magnetic field B. But before moving to the applications of the magnetic field, let's discuss these two quick quizzes. Quiz number 1, rank the magnitude of BDS for the closed path. The path is in the figure below from the least to the greatest. If he said rank, that means we have to calculate for all the paths. But here we have to take care about that magnitude. He's asking about the magnitude or the absolute value of BDS. What will be the magnitude of BDS? As you know, it's mu naught multiplied by the current in the path, enclosed by the path. Okay, here in our figure, we don't have any information about the magnetic field, and we don't have information about DS. So what we can say, to calculate the magnitude of BDS, we have to calculate the magnitude of mu naught I enclosed. So let's see for path A. Where is our path A? Path A encloses all the elements, all the currents. Okay, in the path A, mu naught I enclosed in absolute value is equal to all the current enclosed by the path multiplied by the permeability of free space. But be careful, we have some currents oriented out of the page and some currents are into the page. Here, because he's asking about the magnitude, we don't care which one is positive, which one is negative. But we have to care that if we consider out of the page is positive, we have to consider into the page is negative. Usually, the path is given a direction, a positive direction. If we choose the positive direction counterclockwise, to get the positive direction, the positive current, wrap your fingers or curl your fingers in the direction of the path, and the positive current points outward in the direction of the thumb. So in this case, if we choose the positive direction of the path counterclockwise, out of the page will be considered as positive current, into the page will be considered as negative. In this case, we can say for the path A equal mu naught multiplied by the absolute value 1 ampere is out of the page, so it's 1 positive. 5 amperes is also out of the page, so 5. 2 amperes are into the page, so they will be considered as negative, so we put -2. 6 minus 2 is 4, so we can write for mu naught. We do the same thing for the other paths. For path B is enclosing the current 1 ampere out of the page and 2 ampere into the page. So we can say that for path B, mu naught, I enclose it, equal mu naught multiplied by the absolute value, because he's asking about magnitude, 1 out of the page and 2 into the page, so it's -2. 1 minus 2 is -1 absolute value, so it's going to be mu naught only. Path C. For the path C, it's mu naught multiplied by the absolute value. What is C? Yes, this is C. It's enclosing 5 ampere out, 1 ampere out of the page, 1 plus 5. So it's 6 mu naught. For the path D, it's, what is D? Enclosing 5 out of the page and 2 into the, 5 out of the page and 2 into the page. So 5 minus 2, which is 3 mu naught. Now let's rank them from the least to the greatest. Okay, to do that, which one is the least? The least is path, the line integral of BDS equal mu naught, so B, lower than D. Okay. B, and then D, and then A, which is 4, and then C. We are done. Let's move to the second quick quiz. Rank the magnitude also of BDS for the closed paths in the figure shown below from the least to the greatest. The same question, but we have different configurations. As I said, the line integral of BDS equal mu naught multiplied by I enclosed. We are talking about absolute value of BDS, line integral of BDS. Also, we will talk about mu naught multiplied by the absolute value of I enclosed. However, we have only one current. Let's say this is I. Let's evaluate for path A. Path A is enclosing the current. So what would be the line integral of BDS? It's going to be mu naught I. For path B does not enclose any current. Look here, what's happened to the path B? This is the path B. Is not enclosing any of the currents. So no current inside. So the line integral of BDS for the path B is gonna be 0. Okay. For the path C, also it's enclosing the current, so it's mu naught I. For the path D, there is also a current inside, so it's mu naught I. So how to rank? So we can say that path B is the lowest, and then A equal C equal D equal mu naught I. The path A, C, and D encloses, all of them enclose the same current. However, no current is enclosed by the path B. So what we can conclude from this example, we can conclude that whatever the shape of the path, whatever its circle, square, or irregular shape, so we can say that if the path is enclosing the same current, so the line integral of BDS would be same, regardless the shape, regardless the shape of the shape of the path. Good. Now we have three examples that we will apply Ampere's law. Let's recall that Ampere's law is the following. Line integral of BDS equal mu naught multiplied by the current enclosed. So as I said, this law is valid when the current is constant, steady current, and also we can apply this law if we have a high degree of the symmetry for the conductor, for the configuration of the current. The steps are the following. Step number 1, symmetric path. Step number 2, Ampere's law. Step number 3, left-hand side, right-hand side, and then equality between them to calculate the magnetic field. The first example is the magnetic field created by very long current carrying conductor. So we have a conductor in the shape of a cylindrical conductor. Okay, so the question said a long straight wire of radius r carries a steady current. So the best condition is verified. That is uniformly distributed through the cross-sectional area of the wire. Calculate the magnetic field at a distance r from the center with r greater than the radius of the conductor. That means the radius of the symmetric path is greater than the radius of the conductor. So we are talking about outside, a point outside the conductor. So if we have a conductor in the shape of a cylinder, what will be the path or the line, the path surrounding this cylindrical conductor? So it's going to be, of course, a circle. Okay, it's going to be a circle. Step number 1 for Ampere's law, define the symmetric path. So the symmetric path is a circle of radius r. However, the radius of the circle, because we are outside, is going to be greater than the radius of the conductor itself. Step number 1 is done. Step number 2, write Ampere's law. Line integral through closed path of BDS equal mu naught multiplied by the current enclosed by the path. It's verified. Step number 3, left-hand side. So the left-hand side, this quantity. So as you see here, we have a dot product between B and the line element ds. So dot product means that the magnitude of B multiplied by the magnitude of ds multiplied by cosine of the angle between the vector B and the vector ds. Now, what will be the angle between B and ds? At first, what is ds? ds is the vector tangent to the symmetric path. This is ds. Okay. Now, where is B? B is the magnetic field produced by a very long wire. To get the direction of the magnetic field produced by the very long wire, we have to know the direction of the field lines. The field lines, we can get its direction using the right-hand rule. Put your thumb in the direction of the current and curl your fingers around the wire in the direction of the magnetic field lines. So the magnetic field lines for a very long wire will be circles around around the conductor. And the magnetic field will be tangent to these field lines. So the magnetic field will be tangent to these field lines. Okay. And these are, let's say these are the magnetic field lines, and they are oriented in this orientation because the current is going out. So what will be the angle between B and ds? Theta, it's going to be 0. Cosine theta, of course, will be 1. So this is 1. As long as we are on the symmetric path, the magnetic field is constant in magnitude. So we can put this magnetic field out of the line integral. And we can get that the left-hand side to be equal B multiplied by the line integral through the closed circle, closed path, which is our circle, the path is the circle of ds. What will be the line integral of ds? It's going to be 2 pi r for a circle. So what will be the left-hand side? It's going to be b multiplied by 2 pi r. Done. Now let's evaluate the right-hand side. For the right-hand side, we said it's the current enclosed multiplied by mu naught multiplied by the current enclosed. So how many current we are enclosing? So we are enclosing the total current, which is I naught. So the right-hand side will be mu naught multiplied by I naught. Now what we have to do, this quantity, which is the left-hand side, it's going to be equal to this quantity, which is the right-hand side. And we can say that 2 pi r multiplied by b equal mu naught I naught. So b equal mu naught I naught over 2 pi r. And this is if we are outside the conductor, that means the radius of the path is greater than the radius of the conductor. So we see that the magnetic field is decreasing with the increase of the distance r out of the conductor. Okay, this is if we are talking about a magnetic field outside the conductor. However, we have another case. If we are inside the conductor, what will be the magnetic field? Step number 1, select the symmetric path. Also, it's a circle. However, in this case, the radius of this circular path or symmetric path is lower than the radius of the conductor itself, because we are talking about inside. Step number 2, the right below, line integral of BDS equal mu naught I enclosed by the path. Step number 3, left-hand side, is similar to the outside case. Line integral of BDS equal the line integral of the magnitude of the vector B multiplied by the magnitude of vector ds multiplied by cosine 0. Theta is 0 for the same reason. And then B is constant as long as we are on the symmetric path. So we can write B out of the line integral. The line integral of ds is going to be 2 pi r, and this is the left-hand side. Now for the right-hand side. Here we are not enclosing the total current, but we are enclosing an amount of the current. Let me explain here. If we are enclosing an amount of the current, if we calculate the density of the current will be the current I naught divided by the area of the cross-sectional area of the conductor. What will be the cross-sectional area of the conductor? Because it's cylindrical, so it's going to be pi the radius of the conductor squared. At the same time, as long as we have the same current, it's a steady current, and we have the same material, so G equal the current, an amount of the current I divided by the area of the area enclosed by what? By the symmetric path. Okay, by the symmetric path. Let's write by the path. What will be the area enclosed by the path? Pi, in our case, is a small r, not capital R. As I said, these two quantities will be equal as long as we have the same material and we have the same current. So we can say that I naught over pi capital R squared equal I, an amount of the current, divided by pi small r squared, which is the radius of the symmetric path. What do we need? We need this quantity, I, an amount of the current enclosed by the path. So we can say I equal, at first let's simplify by pi. So we're going to get I naught multiplied by small r squared divided by capital R squared. And this is the current enclosed by the path. Okay, the current enclosed by the path. Good. Now let's come back to our equation. So this is our current enclosed by the path, mu naught r squared divided by the radius of the conductor squared. Left-hand side equal to the right-hand side. So we can say that B equal mu naught I over 2 pi r squared r. Let's evaluate this. The right-hand side or left-hand side said B 2 pi r equal right-hand side, which is equal mu naught I naught small r squared divided by capital R squared. We can simplify by r, and we're gonna get B equal mu naught I naught r divided by 2 pi capital R squared and multiplied by small r. Okay, so if we want, this is B inside the conductor. Do not forget that B outside is the following. B outside mu naught I naught over 2 pi r. B inside mu naught I naught r over 2 pi capital R squared. So if we want to draw the variation of the magnetic field with the distance r, we have a special case when we are at the surface of the conductor. Capital R equals small r. As long as we are inside, the magnetic field is increasing with the increase of the distance r. So it's varying in a linear function. As long as we are going out of away from the conductor, we are varying as a function of 1 over r. Okay, so it's inversely proportional to r. At this point, the magnetic field, how much is it? The magnetic field is maximum, so B max, which is equal at the surface of the conductor when small r equal capital R. When small r equal capital R. So in this case, we're going to get mu naught I naught over 2 pi capital R. Okay, so we are done. This is the case for very long conductor carrying a current I naught. Now we will talk about the second case, the magnetic field created by a toroid. But first, let's define what means a toroid. A toroid is n turns of wires wrapped around a ring-shaped structure. This is the definition of the toroid. You can think of the toroid as a solenoid bent into the shape of a donut. So what are the steps to apply Ampere's law and calculate the magnetic field? Step number 1, select the symmetric path. This is our toroid. Our symmetric path will be a circle with radius small r. Okay, so the symmetric path is a circle of radius r. Second step, Ampere's law. Line integral of BDS through the closed path is equal to mu naught multiplied by the current enclosed by the path. Left-hand side, the same as before. Line integral of BDS is going to be line integral of the magnitude of B multiplied by magnitude of ds multiplied by cosine of theta. Theta also here is 0, so cosine theta is going to be 1. B is constant as long as we are on the symmetric path, so we can say that the left-hand side is equal B, line integral of ds. The line integral of ds for the circle, it's 2 pi r. So we can say that the left-hand side equal 2 pi r multiplied by the magnetic field B. For the right-hand side, I said it's mu naught multiplied by the current enclosed by the path. However, if we look at this symmetric path in blue, how many current we are enclosing? Let's say, for example, this is a current 1, current 2, current 3, current 4, 7, 8, 9, 10, and etc. So how many current we are enclosing? N numbers of currents, because we have n terms. So what will be the right-hand side? It's going to be mu naught multiplied by the number of terms multiplied by the current of the carried by the toroid. Then we can say that left-hand side equal right-hand side. So B2 pi r equal mu naught Ni. So, and then we can say that the magnetic field for the toroid is mu naught Ni over 2 pi r. And that's all. Okay, we are done. So this is the magnetic field produced by a toroid. Now, if we want to get the equation of the magnetic field for the solenoid from the equation of the magnetic field of the toroid, imagine if we break down this toroid over here, and then we open the toroid. So what we're gonna get? We will get a solenoid. What is the circumference of this toroid? It's 2 pi r, 2 pi multiplied by the radius. However, 2 pi r will be equal to the length of the solenoid. So we can substitute 2 pi r in the equation of the toroid by the length of the solenoid, and we can get mu naught Ni divided by the length L. And this is the equation of the solenoid, of the magnetic field produced by the solenoids. Here for the solenoid, we can define the number of turns per unit length. What is the number of turns per unit length? It's the number of loops or of turns divided by the length of the solenoid. And we're gonna get mu naught N multiplied by I, with N equal number of turns divided by the length. So we can say that B for the solenoid is equal mu naught number of turns per unit length divided by length multiplied by the current. At the same time is equal mu naught small n, which is the turn density multiplied by the current I. Okay, so خلاص we are done. But if we want to calculate the magnetic field due to the solenoid using Ampere's law, we can do the following. We can do the following. Good. Okay, step number one. The symmetric path. In our case, the symmetric path is going to be the rectangle with length L and with W. Okay, so the symmetric path for the solenoid what will be the symmetric path? What will be the symmetric path? As I said, it's a rectangle of width of length L and width W. Okay, done. Rectangle A, B, C, D. Okay. Why we choose a rectangle? Because you see that the shape of the solenoid is like a rectangle. So step number two, we write the law. Line integral of BDS equal mu naught multiplied by the current enclosed. Step number three, left-hand side. Line integral of BDS equal line integral of B ds as magnitude multiplied by cosine theta. However, if you see here how many ds we have, ds it's in the direction of the current. This is ds1 for the side number 1. This is ds2 for the side number 2. ds3 for the side number 3. ds4 for the side number 4. What is the direction of the magnetic field? The direction of the magnetic field is to the left. How? curl your fingers in the direction of the current, and your thumb points toward the magnetic field. So what we can say? We can say here it's the line integral from the point A to the point B of BDS1 cosine theta 1 plus the line integral from B to C of BDS2 cosine theta 2 plus the line integral from C to D of BDS3 cosine theta 3 plus BDS4 from D to A BDS4 cosine theta 4. Okay, now we will discuss the angle between DS and B. For the first case, from A to B, DS is going left in the same direction as the magnetic field, which is going left by itself. So the angle between them will be 0. Theta 1 is 0, so cosine theta 1 is 1. For the second case, DS is going vertical, and the magnetic field is going horizontal. So the angle between them is going to be 90. Cosine 90 is 0, so this term will be cancelled. For DS4, DS4 is going left and B is going right. The angle between DS and B is 180 degrees. However, as you see here, the magnetic field is 0 out of the solenoid, so this term also will be cancelled regardless the angle between DS and B. For the fourth line element, DS4 is making an angle 90 with the magnetic field, so this term also will be cancelled because we have only because cosine 90 is 0. So the left hand side will be B line integral from A to B of ds. What will be the line integral from A to B? It's going to be the length L. So it's B times L. This is our left hand side. Let's continue for the right hand side. Okay, for the right hand side, as you see in this figure, we are enclosing how many current we are enclosing? N number of currents. So mu naught I enclosed, it's going to be equal to mu naught multiplied by the number of turns multiplied by the current I, because you see this is current number 1, number 2, number 3, number 4, etc. to the number of loops n. So we can say left hand side, step number 5, equal right hand side. We can say that BL equal mu naught n I. That means B equal mu naught n over L I. As we said before, n over L is the number of turns per unit length, which is a small n multiplied by I. That's all. We are done with the magnetic field produced by the solenoid. Before moving to the magnetic flux, let's make a short summary about these 3 cases. If we are talking about very long wire, B outside the wire will be mu naught I naught over 2 pi r. B inside the conductor will be mu naught I naught over 2 pi r squared multiplied by small r. For a solenoid, for a toroid, B equal mu naught I over 2 pi r, and I forget the number of terms, mu naught and I. For the solenoid, B equal mu naught n over L multiplied by R. And we call n over L the number of terms per unit length. That's all. Okay, we are done. So we are done with the applications of Ampere's law. Now we will talk about the magnetic flux. At first, what is the magnetic flux? The magnetic flux is the following. Total magnetic flux through the surface is the integration of B dA through a surface, through the closed surface. So as you know, B is in Tesla. dA is meter squared because it's a surface area. And the flux will be Tesla meter squared. Tesla meter squared is equivalent to a unit called Weber. So 1 Weber equal 1 Tesla multiplied by meter squared. Okay, so this is our equation for the magnetic flux, for the total magnetic flux. Let's continue. This magnetic flux will be the dot product between the vector B and the vector area A, only if the magnetic field is uniform through a regular surface area. So if B is uniform and we have a regular area, in this case we can say that the flux is BdA. Since it's dot product, so the flux, the magnetic flux will be the magnitude of the magnetic field multiplied by the area multiplied by cosine of theta. Theta is the angle between the magnetic field and the vector area. And the vector area, we recall from chapter 23, is the vector perpendicular to the surface area, and its magnitude is equal to the area itself. Okay, so here, if the magnetic field is perpendicular to the surface of the plane, that means the magnetic field is parallel to the vector area A. In this case, we can say the angle theta how much is 0. Cosine 0 is maximum is 1. So we can say that the flux in this case is going to be B multiplied by the area, which is maximum. However, if the magnetic field lines are parallel to the surface, in this case they will be perpendicular to the vector area. In this case, theta equal 90, cosine theta equal 0. The flux will be 0 in this case, and we can say that the flux is minimum. Okay, well, that's done. So we can use this equation when we have a uniform magnetic field and a regular surface. We can use this equation as the general form if the magnetic field is not uniform or the surface area is not regular. And that's all we have done. We take the last example of this lecture. We have a rectangular loop of width A and length B is located at a distance C from the long wire carrying a current I. The wire is parallel to the long side of the loop. Find the total magnetic flux phi through the closed loop. Okay, let me explain step by step. This is our figure. At first, the magnetic field is produced by what? The magnetic field is produced by the very long wire. If the magnetic field is produced by the very long wire, it's going to be mu naught I over 2 pi r. And r is the distance from the wire, the very long wire, to the point P. Let's say our point P is here. Okay, so if we want the direction of the magnetic field, point your thumb in the direction of the current and curl your fingers in the direction of the magnetic field lines, and the magnetic field will be tangent to the field lines. So in this case, it's going to be into the page from the right side. From the left side, it's going to be out of the page. So from the left side, it's going to be out. From the right side, it's going to be into the page. And that's all. What is the magnitude of this magnetic field? Mu naught I over 2 pi r. That's all. So, خلاص, we are done with the magnetic field. Let's write the equation of the flux. Here, the magnetic field is not constant. Depends on the location of P, because we have this variable r. So our magnetic field is not uniform. If the magnetic field is not uniform, which equation we're going to use? Which expression we're going to use? The line, the integration of B dA through the closed surface. Okay, so here, what will be the angle between B and dA? Cosine theta. Theta, how much? Theta is going to be 0. Why theta is 0? Look at this loop. The magnetic field is into the page, and the vector area is perpendicular to the surface of the loop. So it's going to be into the page or out of the page. Okay, so the angle theta in the two cases will be 0. We will be considered as 0. So we can say that phi equal the line the integration through the closed surface of B dA only. Okay, B, we know B what means. B is mu naught I over 2 pi r. However, dA, how much is it? So as long as the magnet, the point P is moving parallel to the wire, we have the same distance, so this side will be constant. However, if the point P is moving horizontal away or toward the very long wire, in this case, which one is variable? This distance r will be variable. So we can say that the element dA, the surface element dA, is going to be the B, which is constant, and which one is variable? dr. Well done. So now we substitute B by its expression, mu naught I over 2 pi r multiplied by B dr. What is our variable? The r is the variable. So all the other elements will be constant. Mu naught I over 2 pi, and here we have B, the integration through the closed surface of dr over r. From where to where? From where to where it's varying this r through the closed line. From where to where the r is varying? R is varying from this point to this point. So it's varying from C to C plus A. So it's varying from C to C plus A. What's the primitive of dr over r? So it's going to be ln of r. So it's mu naught I B over 2 pi ln r from where to where? From C to C plus A. So we can say that it's mu naught I B over 2 pi ln C plus A minus ln C, which is equivalent ln C plus A over C. That's okay. This is the magnetic flux for this example. We are done. Okay, so here we will introduce Gauss's law in magnetism. We recall that Gauss's law for electricity is the flux, the electric flux, equal EDA, the integration of EDA through the closed surface, which is equal Q inside the closed surface divided by epsilon naught. This is Gauss's law for electricity, but at the same time, we can introduce Gauss's law for magnetism. What is Gauss's law for magnetism? The net magnetic flux through any closed surface is always zero. What is the result of this expression? The net magnetic flux. This statement is based on the experimental fact that isolated magnetic pole, that means monopole, have never been detected or perhaps do not exist. As I said in lecture 28, chapter 28, lecture 1, always we have a bar magnet is coming in the north and south poles. If we break this bar magnet into two pieces, each piece will have north and south, north and south. If we break down also this second piece into other pieces, always we have north and south. So we can say that the monopole does not exist, have never been detected, or maybe it's not existing. And this is the result of the Gauss's law for magnetism. The integration through a closed surface of BdA equals 0. We can say that the magnetic flux is always 0. Now let's move to the class activities. The figure shows in cross-section 3 conductors that carry currents perpendicular to the plane of the figure. If the currents I1, I2, and I3 all have the same magnitude, for which paths is the line integral of the magnetic field is equal to 0. Line integral, as we said in the first example, line integral of BDS equal mu naught multiplied by the current enclosed. Good. For the path A, no current is enclosed by the path A, so the line integral will be 0. For the path B, where is B? We are enclosing I1, so it's a mu naught I1. Okay, all of them have the same magnitude, but as you see, we have some of them are out of the page, some of them are into the page, so we can consider when the out of the page is positive and into the page is negative, so we can say it's, let's say it's mu naught I naught, because here, or we can say out of the page is plus, into the page is minus. Okay, whatever. What I want to say is different to 0. For path C, mu naught, we are enclosing I1 and I2. Let's say I1, I2 out of the page, minus I1 into the page. However, I1 is equal I2 in magnitude, so it's 0. Here we can say it's negative because it's into the page. For path D, mu naught, all of them, I1, I2 plus I3, minus I1. So these two will be cancelled, so we're going to get mu naught I2. Okay, which one is 0? For path A is 0, for path C is 0, A and C. Next. Two long solenoids are nested on the same axis as shown below. They carry identical currents, but in opposite directions. If the magnetic field inside the inner solenoid is 0, if the total magnetic field is 0, what we can say about the number of turns per unit length of the two solenoids? As you know, the magnetic field of the solenoid is expressed mu naught number of turns per unit length multiplied by the current. However, we have two different solenoids. What's the difference between them? The direction of the current and also the diameter. The diameter does not affect the magnetic field. Okay, the diameter of the solenoid does not affect the magnetic field. Which one will affect the magnetic field? The direction of the current, the number of loops, and the length. For the first, let's say this is our first solenoid, solenoid number 1, and this is solenoid number 2. For the first one, the magnetic field is directed to the left. Let's say this is B1. Okay. For the magnetic field, 2 is out of the page, so it's directed to the right. Okay, these two vectors are equal in magnitude, opposite in direction. Why they are equal in magnitude, opposite in direction? Because their sum is 0. Okay, so we can say that they are equal in magnitude. So we can say that B1 equal B2, but opposite in direction. As long as we have the same current, according to the question, but opposite in direction, whatever, identical current. What we can say about the number of turns per unit length is also same for the two fields. Why? Because they are equal in magnitude. Why? Because their sum is equal 0 according to the question. So what we can say about the number of turns, the number of turns are per unit length are equal. Okay. Next. To double the magnetic field inside the solenoid, you should, at first, let's write the equation of the magnetic field inside the solenoid. Mu naught N over L multiplied by I, which is equal mu naught number of turns per unit length divided by, multiplied by I. To double the magnetic field inside the solenoid, you should double the length while keeping the number of turns per unit length constant, double the length. And we keep this quantity, small n is constant, that means N over L. If we double the length, and we keep n is constant, so we have to double the number of turns to get the same number of turns per unit length. If we double the number of turns and we double the length, n will be the same, so the magnetic field will be the same, which is not our case. We want to double the magnetic field. Okay, we want to double the magnetic field, so this is wrong. Double the number of turns while keeping the length constant. Yes, if we double the number of turns and we keep L constant, so that means we are doubling the number of turns per unit length. If we double the number of turns per unit length, that means we double the magnetic field. Okay, so this is true. Double the length and the total number of turns? No. If we double the number of number of turns and we double the length, what we're gonna get? We get the same number of turns. Same number of turns means same magnetic field. So this is wrong. Two of the above, no. None of the above, no. So the correct answer is B. So this is our chapter. Our lecture is very easy. Let's make a short summary. The Ampere's law said the line integral through closed line of BDS equal mu naught multiplied by the current enclosed. For very long wire outside, mu naught I naught over 2 pi r. Inside the very long wire, inside the conductor, mu naught I naught multiplied by r divided by 2 pi r squared. For the toroid, mu naught n I over 2 pi r. For solenoid, mu naught n I with the n is the number of turns per unit length, and we introduced Gauss's law for magnetism. The net magnetic flux through closed surface is always zero, and as a result, the monopole does not exist. Thank you so much, and see you in another recording.